Good morning, everyone. Before I begin today's presentation, I would like to briefly introduce Geo-Lesson. Geo-Lesson is a free educational platform dedicated to promoting knowledge sharing in geotechnical engineering and transportation infrastructure, also including environmental engineering and emerging technologies. Every month, we organize technical webinars featuring researchers, industry professionals, and academic experts from around the world. In addition to webinars, we regularly publish short educational videos through our websites and social media platforms to make technical knowledge more accessible to students, researchers, and practicing engineers. We are also currently working toward launching a podcast series where we will discuss the emerging topics in infrastructure resilience, artificial intelligence, transportation systems, and geotechnical engineering and environmental sustainability. All Geo-Lesson activities are completely free of charge. Our goal is to simply create an open platform for learning and collaboration. Your participation and support encourage us to continue growing these efforts. At the end of this presentation, I will also share this information in YouTube and other social media platforms, and we will be honored if everyone follow us on LinkedIn and Facebook for updates regarding future webinars, technical videos, and podcast releases. Today, Audrika Nahian, will be presenting our work, which is titled Physics-Guided Neural Network for Enhanced Moisture Prediction in Highway Slope Stability Analysis. So now let me briefly introduce myself. My name is Audrika Nahian, and I'm a PhD student and graduate research assistant in the Department of Civil and Environmental Engineering of Jackson State University. My primary focus is on geotechnical infrastructure monitoring, slope stability analysis, remote sensing, artificial intelligence, and physics-guided machine learning applications for transportation infrastructure. Thank you all for joining. Let me share my screen. Can you all see my screen?
Yes, we can.
So this is the title of our study, Physics-Guided Neural Network for Enhanced Moisture Prediction in Highway Slope Stability Analysis. So before discussing the model itself, I would like to explain the engineering problem that motivated this study. When we talk about slope stability, whether it's a highway embankment, a levee, a dam, or a natural slope, one of the most important variable that is controlling the stability is the soil moisture. In geotechnical engineering, we know that soil strength is strongly influenced by water content. As moisture content increases, matrix suction decreases, effective stress decreases, and ultimately shear strength decreases. So this relationship becomes particularly important in expansive clay soils. The study area we used in this research consists primarily of Yazoo clay, which is well known throughout Mississippi and the southern area because of its highly expansive nature. Yazoo clay experiences significant shrinkage during their dry periods, and it swells during wet periods. And as the soil shrinks, the cracks develop, and these cracks basically create a preferential pathway for water infiltration. So whenever there is a rainfall event happening, water rapidly infiltrates through these cracks and increases the moisture content inside of the soil and reduces suction. And as a result, slopes become more vulnerable to instability. For transportation agencies, this creates a major challenge because thousands of miles of highway embankments are exposed to this changing environmental conditions every day. Rainfall, temperature fluctuations, seasonal weather patterns, and long-term climate variability continuously affect moisture conditions within these slopes. So therefore, if we can accurately predict the moisture behavior inside of the soil, we can significantly improve our ability to assess on how to treat the slope before the failure occurs. So this is one of the key motivations behind this work. And I would like to also mention why traditional methods are not enough. Because how do we predict soil moisture? For prediction, we need to get some historical data for that and the soil condition. For most of the cases, we use sensors, but unfortunately, we cannot lay sensors in all of the sections. We have to put the sensors in a point as a point based in within the slopes, and that gives us like 1D data for a specific uh, point location, but it doesn't give us any 2D or 3D idea of where the increment in moisture is increasing or not. So for predicting soil moisture, the first approach is the physics-based modeling, which includes the Richards equation and finite element seepage models. These models are physically meaningful and also scientifically right, but however, they require many input parameters and they often require detailed calibration. Also, they are computationally really expensive, and especially when applied over large infrastructure networks. And uh, for the last few years, the second approach that is very much popular is the machine learning. And machine learning has become increasingly popular because it can identify complex nonlinear relationships directly from data. But there is a lacking using machine learning problems, and that is it only learned patterns. It does not understand physics behind it. So whatever data you provide within the machine learning model, it will give you a data back, but you cannot be sure if that's right scientifically based on physics. So the neural network may produce accurate predictions within the range of the training data, but once the conditions change, predictions can become physically unrealistic, and we do not have any way to check it with normal machine learning models. So the model may produce outputs that violate the known soil behavior. So this creates an I think I'll keep my camera off. So now the study site and monitoring. To investigate this problem, we used data collected from the Terry Road Highway embankment that is located in Mississippi. This site was selected because it has experienced historical instability issues and is primarily underlain by Yazoo clay. The slope geometry is approximately consists of a 15-foot height with side slopes ranging between 3.5 horizontal to 1 vertical and 4 horizontal to 1 vertical. Because the site contains expansive clay and experiences significant environmental variability throughout the year, it provides an excellent location for studying moisture dynamics. Uh, To understand the moisture behavior, we deployed a network of field sensors throughout the slope. Instrumentation was installed at three primary locations: the crest, the mid-slope, and the toe. These locations were selected because they experience different hydraulic and mechanical condition. At each location, sensors were installed at multiple depths. The monitoring system continuously recorded soil moisture, matrix suction, temperature, humidity, and rainfall. The data were collected hourly, and this generated a large data set representing the interaction between environmental condition and subsurface soil behavior. And the advantage of this monitoring approach is that it allows us to observe different parts of the slope response to the same rainfall event. Uh, we also collected the non-invasive geophysical testing data for about 4 years. So that was one of the value that would give us basically a better understanding of the slope. So to discuss the data set that we used for the model development, the target variable we used for the study was the volumetric soil moisture content. And this is the variable that model is ultimately trying to predict. And the input variables included matrix suction, rainfall, temperature, humidity, and several time-based factors. And these variables were selected because they represent the primary environmental controls affecting moisture behavior. Before training the model, several pre-processing steps were also performed on this data. First, missing values were associated with sensor interruptions, and those were removed. And second, outliers were identified using a Z-score with a threshold of plus minus 3 standard deviation. And this step helps reduce the influence of abnormal measurements. And third, all variables were normalized using the Z-score normalization. It is particularly important for neural networks because it prevents variables with large numerical ranges from dominating the learning process. Finally, the dataset was divided into training and testing subsets using an 80-20 split. The model was trained using the 80% of the observation, and the remaining 20% was used to evaluate the model. So before building the machine learning model, it's important to understand the underlying physics content within the data. Several important trends emerged from the monitoring program. First, rainfall events consistently caused reduction in the matrix suction. And this behavior is expected because infiltration increases water availability within the soil pores. So the suction requirement reduces. Second, increases in moisture content typically followed rainfall events. Third, the temperature also influenced the evaporation rates and therefore indirectly influenced moisture behavior. So during warmer periods, moisture loss occurred more rapidly, and during cooler periods, moisture tended to remain longer duration within the soil. So these observations confirm that moisture behavior is governed by both environmental forces and soil physics. So these observations ultimately motivated the development of the PGNN model rather than a purely data-driven model. So we did another feature relevance analysis, which is called the Taylor diagram, to understand the importance of each variable. The Taylor diagram provides us with a graphical way to evaluate the relationship between the variables and the target moisture content. So among all variables, we could see that matrix suction exhibited the strongest relationship with soil moisture. The result is highly consistent with the unsaturated soil mechanics. And suction and moisture are physically linked through the soil water retention curve. And rainfall also showed a strong influence, but the behavior showed mostly as a triggering variable. And it initiates the infiltration events that subsequently alter moisture and suction conditions. These findings provide a strong scientific justification for incorporating the physics of soil water relationships into the machine learning framework. And this leads us directly to the central question of the study, which is, can we guide the learning process using known unsaturated soil physics? And we have seen that the PGNN performs better other than just data-driven machine learning models, and we will see that in the results section. So we have already discussed why physics-guided neural network is important. So we can skip to the architecture of the PGNN model. The model consists of a feed-forward deep neural network. The network basically receives 10 input variables and predicts one output variable, which is volumetric soil moisture content. And the architecture contains 4 hidden layers. For the neural network, the first hidden layer contains 128 neurons, the next one 64, 32, and 16. The gradual reduction in the hidden layers or in the neural count was introduced because it allows the network to progressively extract higher level representation of the data. You can think of the network as gradually learning increasingly complex relationship between environmental variables and moisture behavior. And for activation function, we selected the leaky ReLU function. A common challenge in deep learning is the vanishing gradient problem, and traditional activation functions like sigmoid or tanh can cause gradients to become extremely small during the training. So when this happens, the network learns very slowly. So that's why we use the leaky ReLU, because this helps overcome the uh, limitation. Unlike standard ReLU, uh, it it also includes the negative values or small gradient even when the input's negative. So this improves the training stability and allows the network to learn more efficiently. Now for the prevention of overfitting, because the data set is relatively limited compared to the large machine learning applications, preventing overfitting was extremely important. Overfitting occurs when a model memorizes training data rather than learning the general patterns. So to address this issue, we implemented two regularization techniques. The first was dropout. A dropout rate of 0.1 was used. During training, dropout randomly deactivates a portion of the neurons. And here, 0.1% of the neurons were deactivated. And this prevents the network from becoming overly dependent on specific pathways. And the second technique was the L2 regularization. The L2 regularization penalizes excessively large network weights and encourages simpler, more generalized solution. So together, these approaches improve the model performance. Now for the physical constraint, this is the most important part of the entire framework. This is the physics constraint that we were talking about, and this is the boundary that we provided for our model. So if it tries to generate a not possible scenario or not possible moisture content scenario, this is where the physics comes in. Uh, so the first question was, what physical law should govern the learning process? As our target variable was soil moisture, which is one of the most important input variables in matrix suction, we selected Van Genuchten soil water retention model. So most geotechnical engineers are familiar with this soil water characteristics curve. It describes how water content changes as metric suction changes. So this Van Genuschen equation is one of the mostly used mathematical representation of this relationship. Uh, Fundamentally, it captures the hydraulic behavior of unsaturated soil. So that's why we use the Van Genuschen equation here to recognize that these values are physically connected. So the physical relationship has been validated through decades of experimental research. Okay, so this is basically the guiding principle that we used in our PGNN framework. So now if we talk about the loss function, traditional neural networks usually optimize a loss function based only on the prediction error, the value that it predicted and the actual value of that within that difference. Typically, this is the mean square error or the MSE value, but this model compares the predicted values with observed values and attempts to minimize the difference using the physical constraint equation or the Van Genuschen model. So instead of only just the data loss, we introduced an additional physical loss term. The total loss function becomes data loss plus lambda multiplied by physical loss. So first term measures just the prediction accuracy, which is the similar as the previous traditional machine learning models, but the second term also measures consistency with the Van Genuschen equation. The lambda parameter controls the balance between the data fitting and physics enforcement. And after testing multiple values, lambda value was set to 0.005, where it showed highest uh, similarity with the data. So conceptually, the physical loss acts like an engineering supervisor. The physics constraint immediately evaluates whether the prediction is consistent with the expected suction moisture relationship or not. If the prediction violates Van Genuschen behavior, a penalty is applied. The larger the violation, the larger the penalty. As a result, model gradually learns to generate predictions that are both accurate and physically realistic. So this is the key innovation of the study. So this is the whole PGNN workflow that you can see here. We have this input we had 10 input variables, and there were 4 hidden layers, as we mentioned earlier, and then a prediction was made, and this is called the forward propagation. And after prediction was made, it was tested against the true value, and then the loss function was determined using the data loss and also the physical loss. And after the loss function was determined, the loss was scored. It was using optimizer, and based on weight, it was again given as input for the forward propagation. And this way it continuously kept looping and basically came out with a model that could actually give us a proper result of the input variables to a prediction of soil volumetric soil moisture. So before discussing the results, I would like to briefly explain that we introduced 4 benchmark models: support vector machine, random forest, deep neural network, and physics-guided neural network. So support vector machine represents a classical machine learning approach that has been widely used in environmental prediction problems. Random forest is an ensemble learning technique that is generally very effective for nonlinear dataset. And the deep neural network presents a modern deep learning framework without any physics constraint. And finally, we use the PGNN, or the physics-guided neural network, that represents our proposed or hybrid approach. The comparison allows us to evaluate not only whether PGNN performs well, but whether the addition of physics provides measurable improvements over existing methods. So this is the performance comparison of all of the 4 models that we used. The support vector machine achieved R squared value of around 0.64, and then the conventional deep neural network achieved R square value of 0.86, and the random forest achieved 0.92, and finally the PGNN achieved 0.96. In addition, PGNN also produced the lowest MAE value and the lowest RMSE among all of the models. At first glance, the difference between the random forest and PGNN may small appear. It's only 0.04. But however, from an engineering perspective, this difference is significant. A small increase in prediction accuracy can translate into substantial improvements in reliability when monitoring infrastructure system over long periods. More importantly, the real advantage of PGNN becomes evident when we examine prediction behavior rather than focusing solely on summary statistics. Like if we provide any data range, that is any data to the random forest model, which is closer to the training data set, it will give us a very good result. But if we give a very random number that is way outside from the training data set, in that case, this 0.04 changes in R square value comes in. So in that case, PGNN will handle that data set better than the random forest. So if we further analyze this data, here the SVM produced the weakest performance among all evaluated models. Many predicted values were clustered around a relatively low range. The model struggled to capture the full variability present within our moisture data. Then that is because the complexity of soil behavior. Soil moisture is influenced simultaneously by rainfall, temperature, humidity, suction, and many other effects. So these relationships are highly nonlinear. Although support vector machines can model nonlinear behavior through kernel functions, they often struggle when the underlying relationship becomes extremely complex and dynamic. And as a result, the SVM tended to smooth the predictions. And after that, if we focus on the deep neural network, which is figure B here, it performed substantially better than the SVM. And this is not surprising because deep neural networks are specifically designed to learn complex nonlinear relationship. The DNN here successfully captured many of the interactions between environmental variables and moisture content. However, significant scatter remained around the one-to-one line. This indicates that the prediction error still occurred frequently. Uh, DNN, this is because DNN only learns from data. It has no understanding of unsaturated soil mechanics. So this only recognizes patterns and it doesn't understand the physical laws. After that, if we focus on the C figure, which is the random forest result, the R square value here approached around 0.92, which is the closest to the PGNN model. And this results demonstrates that the strength of ensemble of learning techniques. Random forest constructs many decision trees and combines their predictions. This approach often improves the robustness and reduces variance. So if we look beyond the overall statistics, the weakness of random forest becomes apparent during rapid changes in moisture conditions, as I said earlier. And also, random forest does not understand these processes. It simply partitions data into decision boundaries. And finally, we can look into the physics-guided neural network result, which is figure D. So the PGNN produced the highest R squared value, which is approximately 0.96, also achieved the lowest MAE and RMSE. More importantly, the observed versus predicted scatter plot shows a very tight clustering around the one-to-one line. And this indicates the predictions remained consistent across the entire moisture range. And unlike benchmark models, PGNN successfully scored the highest number for predicting the soil moisture. Okay, so before going to the residual analysis, we could ask, why did PGNN outperform the other models? The answer is in the concept of this restriction. So the conventional neural network searches an enormous solution space. Many possible solutions may fit the data. Some of these solutions are physically realistic and others are not. The network itself has no understanding for distinguishing them, but the physics-guided neural network introduces additional information. So whenever it tries to go outside of the boundary, the physical laws basically says, hey, this is the boundary you have to stay within. So it reduces the loss function like that or increases the loss function based on that. And secondly, that's how prediction accuracy is improved. And secondly, overfitting is also reduced. And third, the predictions become more interpretable from an engineering perspective as actual physics is governed here. So to further evaluate model performance, the residual analysis was conducted. The residual analysis represents the difference between observed and predicted values. A well-performing model should produce residuals that are centered around zero with a minimal variance. The PGNN residual distribution exhibited exactly these characteristics, as can be seen here. Most residuals clustered tightly around zero, and there was very little skewness observed on the left or right. The variance also remained low, so these results indicate that the model produced unbiased predictions. So for the engineering implications, the findings of this study have several important implications. First, physics-guided neural networks provide a practical method for incorporating engineering knowledge into machine learning workflows. Second, they offer improved prediction reliability when compared with conventional data-driven approaches. And third, they are particularly valuable in geotechnical engineering because datasets are often limited. And finally, framework can potentially be extended beyond moisture prediction. And future for the limitations, this model was trained solely based on the Yazoo clay. So in future, if we could incorporate different types of soil in the model, then the model performance would be better and it could be analyzed for any other slope other than only the fat clays or the Yazoo clays. And in this study, we only used one physical restriction, which is the soil suction moisture relation. In future, we could govern other physical like constraints as well, which will be more efficient and which will generate more accurate predictions. And for the final slide of recommendation and future research is additional of physical constraints like hydraulic conductivity functions, seepage behavior, stress-strain relationships could be included in this. And secondly, the framework should be tested using multiple soil types and multiple geographic locations, and the integration of numerical slope stability models could also provide direct factor of safety predictions. So the ultimate goal is to develop intelligent infrastructure monitoring system that is capable of continuously assessing risk in real time. So that is all for the PGNN model from my side, if you have any questions.
Excellent presentation, Africa. Very good.
Thank you, Dr. Khan.
Okay, so wanna go with the question. It would be better to go with like in like discussion session or something instead of the question. So I know it's like, is the topic not like well known to everyone or well understood to everyone. So I think that having the discussion would be better.
Yes, Dr. Barak.
Thank you, Audrika, for excellent presentations. So just I have a few questions. That how many days you collect the data from the ground, and what is the size of the training data?
We collected data for 1.5 years, and we collected the data hourly data from crest to and middle of the slope for 5-meter depth, 10-meter depth, and 15-meter depth. That's one. And what was the second question? I forgot.
Size of your data, especially the training data.
Oh, it was split between 80-20. The training was done with 80% and the testing was done with the remaining 20%.
Oh. Percentage, okay.
Yeah.
Thank you. Thank you.
Is there any more questions?
Yeah, may I ask one question? If no question is there. Zaman is there.
Yes, Bhai.
No, Dr. Tarek, you can go ahead. I can go later after you.
I asked a question. Now you turn.
Okay, so my question is about the data that you collected. So you cleared out the erroneous data with the Z-score filtering, right?
Yeah.
So did you check if that filtering method filters out the plateaued number, like from the data that we have from earlier? We could see that the moisture, the suction sensor mostly gets stuck and it's in the same level for a long period, like 1 year or 1.5 years. So does the Z-score filtering method remove those from your dataset?
Z-score filter, what Z-score filtering method did was it basically determined what most of the values are, and then it created a standard deviation. So if this is the data, like average data that it mostly collected, and there was 3 standard deviation here, it basically took the data from positive 3 standard deviation to negative 3 standard deviation from the average. It filtered out all other data.
Yeah, so my question was, if your average was wrong, I mean, if it, so let's say your data collection was for 100 days So for 70 days or 80 days, your data was stuck. I mean, the sensor was malfunctioning. It was stuck. So that will keep your average at a wrong place, right? I mean, if you do the three standard deviation filtering, it only filters out the spike.
Yeah.
But if you are keeping, if the sensor is flat, I mean, it's not moving at all. So does this method filters those out? I mean, the malfunctioning sensor or anything? I mean, did you check?
Like if the average is wrong, so for when I looked at the data, the suction did not vary much. Like it didn't vary too much. So when there was like +3 standard deviation and -3 deviation, it basically filtered out very random data that was like 10 times or 20 times higher, maybe a misreading. So the
Okay.
average value, I also saw that it got stuck for a long time, but like for other values, it was not too much different.
Oh, okay. So so basically that one was correct value that you assumed, right?
Yeah.
Okay. Thank you.
Okay, let me ask you one question. How this can be connected with the climate resilient research?
So for climate resilient research for infrastructures, we could like for the future recommendations, as we said, that we could use multiple physical constraints there and connecting those to infrastructures and prediction of the climate moistures. We could determine the like what's happening underneath the soil, like how the soil moisture is increasing or decreasing, and we can get an idea of how much closer it is to failure or how safe the structure is.
What is the, how do you envision it? Like it's gonna make the impact? This model, like why this model? Do you think if this model will make better impact than our traditional approach?
Yes, because the physical constraint soil behaves very differently. Like it shows very complex behavior. So if we have a like different types of soil behaves different, shows different kind of behavior. So if we could actually constrain the results or prediction with the physical boundaries like the PGNN used, so it won't give us like random predictions. So that's how it will be useful for climate resilient infrastructures.
Okay, good. So do you think, like my last question, so sorry of asking all these questions. So but my last question is, do you think that using this model we can develop a dynamic soil model instead of the current static approach where everything is like static one time of the training, versus we can have like series of data and new data came in, we can make the model more robust?
Yes, we can. Like Zaman Bhai is already working on that. If we
Okay.
could incorporate multiple soil parameters and we could classify like the soil is shows this behavior. If it shows this behavior, then it's this soil. Then I think it can be done.
Yeah, so I think like this model, we should also keep pushing on this model because this model is a different domain than what Zaman is currently pushing.
Yeah.
Because this one is more on the material side, material behavior side. And if we keep pushing that, then we can create a new constitution model for the submersion.
Yeah. So, I mean, or maybe we can look into other things. So the soil moisture or the pore water pressure, that one is well-known problem. We can try into some more complex things like the deformation model, because I've been struggling a lot with the deformation and I mean, how to predict those. So
if we can solve the deformation problem, then we should deserve a Nobel Prize. So that's a
yeah,
different discussion. But let's go with the submersion. At least that's a easy to do. The deformation would be much difficult because of the lack of the data. Anyway,
Yes.
yeah, it was good presentation. Thank you, Adrika, for all of your hard work.
Thank you, Dr. Khan,
Sure.
for the
All right.
supervision.
Thanks.
May I add on just idea? I don't know how much it is feasible. The satellite image has got a lot of data, soil moisture, long time data. You can get the data for 20 years, even 30 years. As Dr. Khan told that to check the climate resiliency by impact of climate on these aspects, maybe if you add those datas, then we may get the output Dr. Khan is looking for.
And that's a very good input, Dr. Tarek. Especially that data is available, and especially if you do it on the superficial level, not on the deeper level, but on the superficial level, the satellite images can be used very effectively because it's a very matured field that has been developed. So if we can get the data between the rainfall versus the soil moisture variation and then train up the model based on that behavior, I think we can train up a very good model there.
Right. Absolutely.
Sure. All right.
Thank you, Dr. Tarek, for the recommendation.
So I have one last question. What are the problems or challenges you faced while designing the architecture, like solving this problem and the modeling?
One of the major problems was shortage of data. And I think, yeah, that's the biggest problem. That was the biggest problem. Like, if we had more data, we could basically have a larger train test data set, and we could use very randomized data sets for like doing the analysis or the prediction. And also for the transferability of this data set from one slope to the other, that was also very difficult. And I'm still working on it, and if it's possible, then I can maybe show it later. So we have almost come to the ending of this webinar, and those participants who have joined will automatically receive 1 PDH hour. And for those who were unable to join, the video recording will be published in the YouTube and the LinkedIn for your reference. And you can, there will be some PDH questions available in the link. And after solving those questions, you can get your 1 PDH hour. And
بدك بطاريتين انت عندك. بدك بطاريتين. نعم. هاي الثانية اللي انت بدلت.
and we will have our next webinar on the 25th of June, which is the last Thursday of this month. So please, everyone, if you have time, and join and encourage us to keep doing the webinars that we're doing. Thank you very much for your patience. Stop the recording.
Thank you.
Thank you, Adrika.
Thank you.